Yes, Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon. So in this video, I'm going to explain a little bit about the type of DC motor. Actually, I want to simplify just a summary about the type of DC motor. So we have three types. Okay, so one is separately excited, where the field current we have another source, and the terminal voltage we have another source. Okay, it's like a permanent magnet. So permanent magnet, the magnetic field come from the magnet, and the rotor, okay, the rotor will be supplied with the voltage. Okay, so there are two things over here. Okay, so in this thing, so to generate the magnetic field and the permanent magnet, we use a magnet. Okay, however, in some DC motor they use, okay, so some DC motor they use power source, electromagnetic. Okay, electromagnetic. So they have another source over here. So they will do something like coil. Okay, something like this. Okay, so this will be positive, negative. Okay, so this is called as a VF, and this is a VT. Okay, so separate power. Okay, and then this is self-excited, so which means that the connection for the rotor, actually they connect together, either in parallel. So if they connect in parallel, they call it as a shunt. Series, they call it a series DC motor, and also the both combination, they call it as a compounded. And the other type is a permanent magnet. Okay, so this is example of the equivalent circuit. So this is the type for the separately excited. So this is a VF, and this is a VT. Okay, so this is where we supply to the rotor. Okay, so rotor is the armature, and this is field. So field where they generate the magnetic force. Okay, they call it the magnetic flux. Okay, so this is the example. Okay, so we have RF and RA, EA. Okay, so this is just an example. To be more detailed, go to this link and learn from there. Okay, so then as we know before that the magnetization curve, where this curve actually is the flux, magnetic flux versus the magnetomotive force. Okay, so you can see that the magnetic flux is proportional to the magnetomotive force. Okay, same go to here, where the EA is proportional to the IF. Okay, it's proportional. So there is no direct equation. There is no direct equation A to F, EA to F. There is no direct equation. But anything happen, any change in IF, so you need to refer to the graph. Okay, you need to refer to this graph. Okay, or maybe the like DC motor data sheet. Okay, like a data sheet. So normally they will have the relationship. So the relationship they will have here. So anything change in IF, so you need to refer to this graph, and then for example IF is here, and then you need to do like this. Okay, and then you can get the value of EA. Okay, so any change you need to do something like that. Same goes to the flux and also the magnetic force. Okay, so this is the separately excited DC motor, as I mentioned before. So we have a R adjusted, so where we adjust the current flow. Okay, however, we can ignore in calculation, we can ignore this, and also the inductance over here, we can ignore it. So then to calculate the IF, so we just use the Ohm's law, normal Ohm's law, V equal to IR. Okay, so this one is IF equal to VF over RF. Okay, so in this here, in this right side, so we just use the Kirchhoff voltage law. So we use the Kirchhoff voltage law, and then we will get this, we can get this equation. Okay, so as we can see from here, Vt is given. Okay, Vt is given. Okay, and Ea we can get from the graph. Okay, from the graph. Okay, the previous graph, and this one is given. Okay, Ra is given, and Ia is can be calculated. Okay, this one is calculated. Can be calculated. Okay, so it will be like this. Ia equal to Vt minus Ea divided by Ra. Okay, so and then IL equal to the Ia. Okay, so then this is the shunt DC motor. Okay, so it's connected parallel to the rotor. So this is the field, okay, where the magnetic field come from, and then this is the rotor circuit. Okay, so from here also we can see that since the parallel, so this is Vt, so you do a Kirchhoff voltage law, you can get the same equation like before, this one. Okay, and to calculate the IR, so at here this is not a Vf but this is a Vt. So be careful, this is a Vt. Okay, so this one you can ignore, and also this one also can be ignored. So just Vt divided by Rf, you can get the If. Okay, so since parallel, so you can see over here this is Il, so they will separate into two. So Il equal to Ia plus If. Okay, so then the terminal characteristic of the DC shunt motor. Okay, shunt DC motor. So what happen when the motor is rotating and then suddenly you put some load? Okay, you put some load over there. So what will happen? Okay, so the first thing that will happen, okay, so when you put some load, okay, to the rotating motor, okay, the first thing that will happen actually is the torque load. So the torque load is this is the DC motor. Okay, this is the shaft. Okay, so you put something. Okay, maybe you hold or you put some friction over there. So this is the torque load. Okay, so whatever motor produce, they call it as a torque induced. Okay, so once you put some load, okay, when the load is increased, the torque load also will be increased. Okay, so at first, okay, before you put the load, okay, the torque load will be equal to torque induced. Okay, this is normal situation in the steady state. Okay, then you put some load. Once you put some load, the load will be increased. Okay, then what happen? So the torque load will be more than torque induced. Okay, then once this happen, so the motor will start to slow down. Okay, so what happen when the motor slow down? So we see from the equation, the Ea will be affected because this is the rotor shaft, the shaft of the motor rotation. So when the speed goes down or decrease, so Ea will be decreased. Okay, so as I mentioned before, the Ia is equal to Vt minus Ea by Ra. Okay, so when the Ea goes down, okay, so Ia will be increased. Okay, so this will be increased, Ia will be increased. So as Ia increase, the torque induced will be increased. Okay, why the torque induced will be increased? Because the torque formula is equal to K phi Ia. So when current increase, the torque will be increased. So they will keep increasing until they reach the steady state position, situation. Okay, until they come to the steady state condition. Okay, so now with lower mechanical speed compared to before you put some load. Okay, so from here we can try to replace. So you know that before Vt equal to Ea plus IA RA. So we replace IA, so we replace EA with this equation, okay, and IA we replace with this equation, okay. So where this equation we replace, and then we will get Vt equal to K flux omega plus torque induced minus K flux times with Ra, okay. And then we try to simplify. We want to find the relationship between the speed and torque, okay, the speed and torque induced, okay. So we just want to see the relationship. So if I plot the graph, so the graph will be like this, okay. So this is omega, this is the torque. So the more the higher the torque, the lesser the speed, okay, the slower the speed, okay. So if you want to speed higher, so the higher the speed, the lower the torque, okay. Okay, so in this example, so please open from this video, so they will explain everything, okay. Then I really hope that you can go to the nonlinear analysis DC shunt motor. Okay, then so how to control the DC shunt motor speed, how to control the speed of DC shunt motor, the shunt DC motor. So there are two methods. First, adjusting the field resistance, so the RF, and also the second one is, okay, the second one, adjusting the terminal voltage, okay, the VA, okay. So just now we didn't see where is VA, so later on I will show you. Okay, so this is the this shunt DC motor equivalent circuit. So you can see over here there is a RF over here, and then others is like the same, okay. So in order to change the speed, we can change this point, okay. As we know that the IF is equal to VT over RF, okay. So what happens when you increase the IF? So when you increase IF, then the IF will be reduced, okay. So then you look at the graph, IF with EA. So you can see this is like this, okay, the relationship. So you reduce, and then so when RF reduce, EA will be reduced, okay, EA also will be reduced, okay. Then what happened when EA reduce? Okay, so when RF reduce, when EA reduce, okay, so when EA reduce, actually speed will be reduced, okay. EA reduce, and then IA will be increased, okay. Or I start again, so IF VT over RF. So when RF increase, IF will be reduced, okay. So once you reduce this one, the magnetic field, okay, the current for the magnetic field, so the flux also will be reduced, okay, the flux also will be reduced, and then the EA also will be reduced, okay, EA will be reduced, okay. So when EA reduce, what happened to IA? IA equal to VT minus EA divided by RA. So when EA reduce, IA will be increased, okay. So what happened when IA increase? Okay, so you can see the torque induced is equal to K phi I IA. So when IA increase, the torque will be increased, okay. So yeah, sometimes we can see the increasing, okay. Over here they put the reduce, so this one even though the flux reduce, but IA will be increased higher, okay. So yeah, it's difficult to show you in just an equation, but in formula, if you go to this part, and then you can see the example, okay. So yeah, even though that the flux, okay, so even though the flux is reduced by 1%, okay, even though just reduced by 1%, but IA will increase 49%, okay, as I mentioned before over here, okay, the flux reduced 1%, but the IA will increase 49%. So then torque induced will be increased. Okay, so when torque increase, okay, torque induced is more than torque load, so motor will speed up. Okay, motor will speed up. Okay, motor will speed up. Okay, motor will speed up over here. So they will keep on increasing. Okay, the torque will keep increasing until they reach the until they reach the steady state condition. Until they reach the steady state condition. Okay, so they will increase. So then since motor will speed up, okay, so they will go back again. So when motor speed up, so you need to see over here again. So motor speed up, and then motor will speed will be increased. So when speed increase, so EA will be increased. Okay, so EA increase, IF will be increased. Okay, until they reach the this level lah. Okay, so really hope that you can understand lah. But however, in this case, even though the similar is torque, but in higher condition, higher speed compared to before you change the RF. So this is how to change the motor speed. So if you want to speed up, the increase, okay, to speed up increase, okay, to speed up the to increase the speed, to increase speed, then increase RF. Okay, this is one of the way. So same goes to inversely. So RF, reduce RF will affect to the reduce speed. Okay, okay, then this is the another method, the second method, which is the changing the armature voltage. So changing the armature voltage, actually we cannot directly change. We need to have the controller, the variable voltage controller. Okay, so in this point we supply another voltage, and we supply the terminal to the motor, and then before to the rotor we have another controller over here. So, okay, so then we can measure over here. So this is VA. Okay, this is the VA. Okay, so by changing this, controlling the VA, okay, controlling the VA, we can change the speed. Okay, for example over here, when the VA is increased, okay, so we know the equation IA equal to VA minus EA minus RA. So just now this is VT. Okay, so you can see before is VT because it's parallel, so now it's VA. So it's not parallel anymore. So actually we take this point. Okay, so if is variable voltage controller is not there, okay, then VA equal to VT. Okay, so what happen when VA increase? So when VA increase, IA will be increase. So when IA increase, the torque will be increased. Okay, so when torque increase, it make torque induced more than torque load. Okay, and then the speed will be increased. Okay, so when you increase the torque, okay, EA will be increased. So EA will be increased. Okay, so then when EA increase, they will decrease the IA. Okay, so after IA decrease, so they will decrease the torque until they reach the equivalent condition, or the steady state condition. So now with the higher speed. Okay, so by increasing, you increase VA, it will affect with increased speed. Okay, reduce VA, so it will reduce the speed. Okay, reduce the speed of the motor. Okay, so this is the more detail about the explanation about the DC motor. Okay, so I really hope that you can go to this video to read the to get the explanation about the this example. Okay.